Hi everyone, welcome to my short presentation of my undergrad thesis. So the name of my thesis was that a semi-supervised machine learning approach for open star cluster mean by determination. We will go over like a small backgrounds. So first, what is the open clusters? If we say very simply, then we can say like when a group of stars born from the same molecular cloud, they are called the star cluster, and because they form from the same molecular cloud, what happens is that they usually have similar structure, like similar chemical chemical composition, and also similar age, and they usually hold together by their mutual gravity. So that's why usually they are stay in the similar position in the sky. Their distance is also same for us, like almost for all of the stars of the clusters has the similar distance, and the velocity across the sky is also similar. So these are the main properties of an open cluster. And then a small background of a machine learning model, that we can divide the machine learning models in two parts. Like when we have like level training data, like suppose in our example we know the properties of the stars, and we also know that which one are the member and which one are the not member, so we have the labels. So if we have the label training data, then we can use like supervised machine learning models, for example random forest or artificial neural network, those kind of things. And if we don't have the label of our data, we only know the properties of the stars, but we don't know like which are actually the member and which are not member, then we need to use some kind of like unsupervised machine learning model. For example, Gaussian mixture model, or there is something called DB-scan algorithm, or like upmask. We can use those kind of like machine learning model if our training data doesn't contain the labels of our stars. So in the literature review, what we found is that most of the works that has previously done to find out what are the members and what are not the members of a particular star cluster, they use like unsupervised model. Like they used it because most of the time we usually have the properties of the stars. We don't know just direct from the observational data that which one are the member and which one are the non-member. So you had to use unsupervised method. So that's one of the limitations that we have in the current study of this field. But in the machine learning models, we also found that the supervised model is usually more accurate, and it's more easier to validate because we know a ground truth. So we can compare our result of the model or prediction of the model with the ground truth to validate our model even better, which is tough to do in the unsupervised model. So that's one. And also very recently there are a few papers, 2 or 3 papers, who used an additional supervised models to find out the members of the open clusters, and they all of these models, all of these 2 to 3 papers, they found like more members compared to the previous studies. So that also suggests the idea that maybe adding an additional supervised model could be very efficient in this particular context. So based on this evidence, my hypothesis is that like a combination of unsupervised and a supervised model would be a better approach to detect members of star clusters. And what do I mean by better approach is that two things. Like one is ideally we would get like more members, we will able to detect like more members, and secondly like our models will be like our model performance will be better compared to the previous ones. So these are the two criteria that we're measuring the better approach in our hypothesis. So due to the time and like limit, like resource constraint, like what will be the specific part that we will focus in our in my like what are the specific part that I focused on my like undergrad thesis is this 3. So the goal of my project was to first develop a workflow, like how we will actually combine the unsupervised and supervised models. So actually developing is like a systematic strategy that can be easily followed by like other people to like build upon on that. So developing a workflow was the first one. And secondly, like developing or suggesting metrics that we need to use for comparing between different models. Like if we wanted to find out a good unsupervised model or a good supervised model, what will be the good metrics to use? So developing those matrices was the second part. And then the third part was that whenever we are applying any type of specific model to this particular context, what will be the best practices that we need to do for applying that model in this particular problem. So in my like capstone project, in my undergrad thesis, like I only chose 2 models to explore. Like from the unsupervised model realm, I used the Gaussian mixture model, and for the supervised model realm, I used the random forest. So these are the 2 like model algorithm I explore to see like how the workflow will work and what are the matrices should be what will be the best matrix to use in this particular case and what are the best practices. So do all those three scopes of the project. And just before jumping into the actual project method, like we also need to think about like why it matters and why it matters now. So ideally we need to know very confidently which are the members of our star cluster, because when we know like the confirmed member, it helps us to do like further studies using the properties of the member of a cluster. For example, like we can, if we wanted to find out like understand like how the star form, usually most of the star form inside of a cluster. So if we know the dynamics of the clusters, it helps us to understand like how stars actually form. And depending on like where in the galaxy the clusters are located, it also helps us to identify like how the galaxy is formed and how the galaxy is evolving over time. And similarly, just like the galaxy, like we can also like map out how the star is evolving throughout its lifetime by studying the properties of the cluster member. So that for doing all of those, I need like confirmed members. And second point, that very recently we now have a like Gaia mission from European Space Agency that gives us very precise data for the distances and the positions and the velocities of the star. So we didn't have those precise data available before that we now currently have. So using those precise data, we can now do better job to identifying the members for different clusters. So that's why it could be very good thing to do right now. So now the first part of my project is the workflow, how I'm like planning to combine the unsupervised and the supervised model together. So first, whenever I will work with a specific cluster, first I will choose a very small region around the cluster center, and then I will apply unsupervised model. So the unsupervised model will take input the properties of the stars from the smaller region. So because I am taking a very smaller region, we will get more confident result using unsupervised model, because there is less chance of having like field star contaminations, because we are taking very small radius. So maybe we will take only 30-second radius or 30 arc-minute radius around the cluster center, and then we apply the unsupervised model. So the unsupervised model will use the properties of the stars to tell us what are the possible members and what are the not, like what are the possible field stars. So ideally we will get a binary output, either 0 or 1. So now for at least a small sample of stars, we have a potential level, like are the member or field stars, and we know their properties. So using these properties and the levels, now we will train a supervised model, and this supervised model will be using the classification, because our levels are like binary levels. We only have like members and non-members. We don't have any continuous like number. So that's why we cannot use like regression. We need to use like classification supervised model. So once we trained our classification supervised model using those training data, then we will apply this model to a further region, maybe like 2-degree radius or 2.5-degree radius, so to a larger region, to find out, okay, what are the stars we have in this larger region which actually have the similar properties compared to the similar to the like member stars. So because now we have a supervised model and we have a ground truth, we can compare our model, or we can validate our model even better, even in the larger region. So now using the supervised classification model, we will find out the prediction, which will be a classification prediction, right? Which will be still be binary output, either 1 or 0. And then from the binary output, we will like convert them into a membership probability, so that people can use it on their own purpose, like depending on the purpose of the research. Like maybe they can use a more lenient cutoff, or maybe more strict cutoff to like find out what are the members and what are the field stars. And like one way we can do it is maybe we can like bootstrap, like we can bootstrap a data sample and like apply the same model several times and see like how many times a specific stars is being classified as a member or not. So this is one way to do it. So this was our workflow. And in the matrix part, like for the supervised model, we use precision, because our one of the things that we need to consider is that we want to avoid as much as possible to have like false positive, like we are saying that this is a member, but actually this is not a member, this is actually field stars. We don't want that type of situation to happen, because if we misclassify a field star as a member stars, then what will happen is in the further studies, people will use that star as a member of the cluster, and that can deviate their results in the about the star cluster property, something like that. Like it's still okay if we classify a member stars as a field stars, then in worst case scenario, what will happen is people will not use that member to do their analysis, to their further analysis, because it is classified as a field star. So that will not necessarily hamper the analysis itself very much. Maybe the sample size will be a little bit smaller, so that's the only consequences, but the result will still be accurate. But if we say a field stars and say that it's actually a member, then the problem will be that the people will use these field stars as the member stars, which will deviate their results. So that's why we use precision, which avoid like false positives. The exact formula was that we will use the true positive divided by the true positive plus false positive. And for the unsupervised train, usually one of the common method people use is like the Silhouette score, which usually take into account like how the differences of the like how different clusters of my model, how different group of the stars of my model is distant with each other, like how far away they are located. This is the one way people use Silhouette scores. But in our cases, like we focused more onto the idea of like the variance, the idea of the standard deviations, like because we are assuming that the member should be more compact. That means they should have very smaller standard deviations compared to the field stars. The field stars should be uniformly randomly distributed, so they should have a very higher standard deviations. So based on that assumption, we used a modified version of the Silhouette score, where instead of the distances, we use the variances, or more exactly, we use the standard deviations. So for all of the like if we have k features in our feature spaces, then we'll take the average modified Silhouette scores of all those features, and the average and the modified Silhouette score is calculated using this formula, like the ratio of the difference between the standard deviations of the field stars and standard deviation of the member stars divided by the maximum of these two standard deviations. So having this specific formula helps us to keep the matrix in between -1 to 1. So we know if we have a model with 0.8, then we know, okay, it's maybe very good because the highest it can be is 1. So 0.8, 0.9 could be a very good choice to have for the matrix. And of course, like we can do like empirical study to find out, fine tune like exactly what matrix, what will be our cutoff for a good model and bad model, that we can always do using the empirical data. So that was our matrices. And then the third part, what are the like practices, best practices that we can do when we're applying specific models in this problem is the following. So for the unsupervised model, for example, when we explored the Gaussian mixture model, we first replicated a previous study that has been done on the Gaussian mixture model, and then we modified certain criteria to improve the justifications and improve the like efficiency of the model. For example, one way is the feature selection. So what features will be useful to our model? So how we can do it is maybe we can find out what are the assumptions of the model, and based on the assumptions, maybe we can see is it possible to use certain type of features, or it will be problematic to use certain type of features. For example, for Gaussian mixture model, we remove the array and deck from the feature space. Why? Because one of the assumptions of the Gaussian mixture model is that if a specific feature is overlapped between the two groups, like the member and non-member, then Gaussian mixture model cannot distinguish between these two. So as we can see, like when we have a potential member and non-member, like they all align, overlap, in especially for a smaller search radius. It makes sense because we have a like a specific cluster center, and then we take a cone search around this cluster center. So we have a large number of stars on the cluster center, and then as we go further away, the number of stars decreases. So for field stars and for member stars, for both of them, we have a large number of stars along the line of sight of cluster center. So that's why their their peak point overlap with each other. So that's why it's better to avoid the array and deck. And we also found that removing the array and deck from the model actually improved our like modified CLOT score, the MSS metric. So secondly, we also sometimes need to maybe apply some of the, maybe we need to optimize some of the parameters, or maybe we need to add some specific threshold or cutoff to certain, like maybe certain parameters of our model. For example, in the Gaussian mixture model, like we need to apply a distance cutoff. Like if we, the problem with the Gaussian mixture model is that one of the limitation of Gaussian mixture model was that we cannot give a very short range of distance, and either we cannot give a very large range of distances. For both of these extreme cases, like Gaussian mixture model failed to distinguish between the member and field stars. So we need to always find out an optimum range, where the optimum range of distance cutoff, where the Gaussian mixture model gives us the better results. So what we did is we tried with different cutoff for the distances, and then for each of the cutoff we find out what is the MSS metric, and based on that we find out optimum metrics. As you can see from the graph, like when the range of the distances started to increase, ideally the MSS matrix has also started to increase up to an optimum level, which was around 550 parsec. So based on the graph, based on this empirical evidence, we use 550 parsec as our distance cutoff. So like if we know from the literature that the distance of this particular cluster is maybe 1000 parsec, then our distance cutoff will be, we will only select the stars which are between 1000 plus minus 550 parsec. So maybe from like 450 to like 1550, 1550, yeah, 1550 parsec. So in this range, so we can use the MSS to, like in the similar way, if we need to add cutoff for other parameters, we can use the MSS metric to do that. And similarly, the third part was that when we will, for some of the model, for example, in Gaussian mixture model, we usually get output as a membership probability, right? So then we need to use a member cutoff, like, what will be our threshold to find out, okay, these are our members and these are our non-members. Should we use a 0.5 cutoff, or should we use a 0.8 cutoff or more strict cutoff? So we need to like justify our choice of member threshold. So this is another thing where we can also again use the MSS metric. For example, in this graph, we try with different cutoff and see like which cutoff gives us the highest MSS value. And then we found that 0.95 cutoff is the one where we're getting the highest MSS value. So we take all the stars which are greater than 0.95 membership probability as our member stars. So we can use this for also, we can use the MSS metric also for that. Similarly, for supervised model, we can also think about how to build the best practices. So first is the feature selection. So there are several ways we can select which features is important in the supervised model. So we compare between like 3 different type of like feature selections model, and then we selected the sharp feature importance, which work better than the other two. Like the by default choice of the feature selections mode is that maybe we try to define features and then find out for which combination of features which we have a like highest value in the metric. So that's one criteria to do it. But another criteria to it is using the sharp feature importance. So if we use sharp feature importance, it tells us like exactly like what will be the like average impact of each of the features in the model itself. So if we don't use the model in our, if we don't use the feature in our model, then how the output actually changes. So depending on that, what we did is, once we get the feature importance value, we normalize them. We normalize them to make sure that the cumulative feature importance goes from 0 to 1. And then we use a 95% cutoff, 95% threshold. So we only use those features that we needed to cross the 95% cumulative feature importance. For example, here, we only use like the first 1, 2, 3, 4, 5. We can use the only most important, like the 5 best important parameters in our model to cross the 95% threshold. So the other ones were actually not that much necessary. So we removed that from our model. So this is how we did our feature selections. And then secondly, another thing we need to always consider is that it's possible that our data is maybe not balanced. And because our data is not balanced, like when we divided the data into the test and training data set, we also need to make sure that every subset have the same ratio from the original model. So we need to use the stratified split instead of the normal splitting of random splitting. We need to use the stratified random split to make sure that the class distribution is just the same in our test data set, test subset, and also the train subset. So that's also one thing we need to consider. And for optimizing the hyperparameter, we can use cross validation in the supervised model. That's easier. Like we can find out what are the parameters that we need to like optimize and what will be the possible ranges of value that these certain parameters can have. And then maybe we can use a random grid like search, where we will maybe we can select like we will do 100 random search. So in each of the iterations, we will select a random value from the range of these parameters and then run the model and find out what's the metric value for our validation set. And based on that, we can find out what will be the best set to use, what will be the most optimized parameter to use in our model. For example, in our particular cases, like we can see in the right of the screen, we have those values for the number of estimators is 500, minimum sample sensitivity is 5. Those are the values that we got, which resulted the best result in terms of the matrix, which is the precision in our cases in the validation set. So these are the practices that we can do while applying supervised model and also unsupervised model. And finally, if we see our result, so this is our result. We can see that in terms of the matrix, like the direct replication was the replication that has been done in the past studies, and our analysis was the modified replications we did for two particular cluster, M67 and NGC3766. We can see for both of the model, like the MSS metric is moderately very like high, especially for M67, it's very strong. Like we can say our model is performing very nicely, 0.91. And for 3766, there is still room to improve upon it, but maybe with we only tried with GMM. So only with GMM, the best we can get is 0.78 MSS metric for NGC3766. And we can see like the precision was almost perfect for both of the model in both training data and test data, which shows that there was no overfitting happening. And finally, these are a number of members that we found. So we found like almost like 1,400 members, 1,500 members for M67 and more than 6,000 members for the NGC3766. When we compare it from the state of the art model that we currently have, which is the Kantar-Cowden paper, which is the best paper we have in the open cluster study, open cluster field. They reported number of members was only even less than 1,000 for M67 and like a little bit more than 1,000 for NGC3766. So we can see that we can have a large improve on the, at least from the number of members. And also we can see that now we have a more solidifying numbers, quantifying metrics that we can use to like define if our model is strong enough or not, something like that. So now if you see the pictures, so I plotted the untapped members, which is the state of art model right now, and our analysis members. As we can see clearly is that we found more members, especially on the outskirts of the clusters, where it's harder to find members, and then also around the fainter region. You can see in the third picture, and the y-axis we have the magnitudes or the brightness of the stars. So the fainter the star, we like most of the blue models, blue stars, most of the new blue stars are found into the fainter region. So these were the stars which is less brightness. So it's still like harder to find out from the previous model because maybe the lack of precision data that we had previously. Similarly, we can see also that for the NGC3766, we have found like more members into the outskirts of the cluster and also in the fainter region of the cluster. And then finally, our conclusion is that it's possible. It's a very potential model. Like if we can use a semi-supervised model, like a unsupervised model, and then an additional layer of supervised model, it shows at least from this preliminary, this exploratory like analysis is that more members can be found under the outer sky region and also into the fainter magnitudes. So to improve upon our model, what we can do is we just try it with two different models, like one unsupervised and one supervised. But ideally, what we wanted to do is we can compare between a number of unsupervised model to find out the best unsupervised model, and then also again compare between a number of like supervised model to find the best supervised model. Then we'll combine these two to find out the most optimal model possible in this particular context. And then around like regarding the best practices for unsupervised model, we can use the MSS metric to do the feature selection or like hyperparameter optimization things. And for the supervised model, we can use like sharp feature importance for selecting the features, and then we can use the cross validation for optimizing the parameters. So thank you very much for listening. If you have any questions, like please feel free to contact me. My email is like mahmud.nobe, mahmud.nobe @uni.minerva.edu. Thank you very much.